So, good morning to one and all. The screen is visible now. Anyone please reply?
Yes, sir.
Which slide is visible? What is the title of the slides? Can anyone tell?
Types of digital voltmeter.
Okay. So we have discussed in the previous class about the basic construction and working of the digital voltmeter. Okay, we have discussed construction and working of digital voltmeter. This is the actually working method. It attenuates analog to digital converter. It is going to count the triggers and it is going to give the readout value here. Now, based on the output here now, so the method which one we are going to use, the analog to digital conversion method, which one we are going to use. Based on that, we have classified the digital voltmeters into 5 types. First one is RAM type digital voltmeter. Second one is integrating type. Third one is potentiometric type. Fourth one is successive approximation type. And fifth one is continuous balance type digital voltmeter. We have classified here. Now, one by one, we will discuss this one. So the RAM type digital voltmeter here now, that is called, it is the voltage to time conversion we are going to call. In the period of time we are going to consider, because we are going to use the time counter, we are going to use oscillator here now. So whatever the voltage is there in time conversion, we are going to measure that one here. See, this is the block diagram of the RAM type digital voltmeter here now. So why the name came here now, ramp type means the heart of this instrument is ramp generator only. The heart of the instrument is ramp generator. So for that reason, we are going to call this one as ramp type digital voltmeter. So we are going to call that. This is a ramp type digital voltmeter here. So how we have to do here now? So see here the ground we have taken here now. With respect to the ground, we have given the DC input here now. Whatever the voltage is there, we are giving here. This is the input. The ranging and attenuator block, what it is going to do, the ranging and attenuator, see here, amplifying and attenuates, we are going to call that one here. If the signal is very low, so by amplifying that one, we are going to make that signal into large signal here as per the requirement. If the signal is very high, so we are going to bring that one into lower value here now. For the normal value, we are going to bring that one here now. So amplifier, low signal to the large signal, that is called amplifier. Large to lower signal, that is called attenuator, we are going to call here. It is going to attenuate if the signal is large. If it is going to amplify if the signal is low here now, that output of this ranging and attenuator is given to the comparator here now. It is going to compare the which input here now. Whatever the input is there, this input, it is going to compare with the ramp generator signal we are going to take here now. So the ramp generator signal it is going to take here. So then it is the comparator will compare and it will give the output here to the gate pulse here. Now this is one method. Okay, it should have to on or not. It should have to give that one. It is continuously here now. So if the input and ramp generator is comparing and it is going to give the output, the signal will start to flow over there. So output we are going to get here now. So that is, it is going to give the start pulse here now. It should have to start pulse, it is going to give here now. But the ramp signal, another input is given to the output is given to the ground comparator here. Now it is going to compare with respect to the ground, it is going to compare. If the ramp signal is reached its value, it should have to bring back to the 0. On that condition, stop pulse will be produced by this comparator here. The stop pulse will be produced here now. So this stop pulse, what it will give, the gate is there here now. It is going to close the gate here now from the oscillator here now. It is going to close the gate. If the gate is closed, then there is no output at all. That is going to decrease here now. So the counter, it is going to count the impulses here now, and it is going to give the value here. This is sample rate multi-vibrator we are going to call here. Multi-vibrator. Directly it is connected to the counter. How we are going to use this one, and ramp generator we have connected here now. After completing the cycle and work, it should have to reset purpose we are going to use here. This is going to multi-vibrator. It is going to reset the pulse generator, or not, sorry, ramp generator and counter. It is going to reset. So this is the simple operation of the ramp type digital voltmeter here. This is the simple operation of ramp type digital voltmeter here. Now, there is no thing, extra thing is nothing here. Only you have to diagram explanation you have to do here. Same thing, whatever I have explained, I have written here now. The block diagram shown is the ramp type digital voltmeter. This block diagram. There is a ramp generator. This is the ramp generator, which this is generating a waveform which is representing a ramp here now. Like a ramp, it is going to generate the waveform here now. The heart of the circuit is ramp generator. Therefore, it is called as ramp generator. This is in this one, the input it is going to compare with the ramp generator output only. The input is going to compare with the ramp generator output only. So what we are going to call, this is the heart of the block here. No, so the name came, that is called ramp type digital voltmeter. So the input which should be measured is given at the input voltage here. Whatever we want to measure, we have given at this point here now. So this input is fed to ranging and attenuator circuit. It is going to give to the here, and what it is going to do here now, will amplify the signal if the signal is small. If it is small, then it is amplified. If it is signal is large, it is going to attenuates that one here now. So attenuator will attenuates. It is ranging is nothing but amplify here now. So next, the ground comparator. This is the ground comparator here now. Where it went? Okay. The ground comparator will compare the ramp signal and ground output is given for the stop pulse here. Now, this is the ground comparator. This is the input comparator. It is input comparator. Input is compared with the pulse ramp generator. Then the start pulse is given here now. And this ground comparator, the ramp generator signal is compared with the ground, and it is equal. Then it is going to give the stop pulse over there. So this output will stop the flow of purchase from the clock oscillator by closing the gate here. Whatever the clock oscillator is there, the time, in the form of time, we are going to get the signal voltage in the form of time we are getting here now. So this clock operation by oscillator, it is going to stop by closing the gate here now. So the operating principle of ramp type voltmeter is to measure the time that a linear ramp voltage takes to change from the level of input voltage to the zero voltage, or zero to input voltage, whatever it may be, larger to zero or zero to larger, vice versa, we are going to call here. This time interval is measured with an electronic time interval counter, and counter is, it is going to, this is the counter is there, this is electronic counter we are going to call. This count is displayed in the readout block here. It is going to, whatever the oscill times duration is there, that one it is going to count here now, and that count is given to the readout block. That readout block, it is going to give the output here. So this is the simple operation working of the ramp type digital voltmeter here. So only block diagram explanation, how to do this one. Any doubts here? Any doubts? Any doubts? I'm asking to you people only. If
No,
you
sir.
have any doubts, yes. Any doubts? अरे कोई तो रिप्लाई दे दो, शर्माने के बाद नहीं। हाँ?
No, sir.
ना आधा घंटा लेते क्या टाइम रिप्लाई देने के लिए? So the next device that is called integrating type voltmeter we are going to call here now. So here we are going to use the integrator here now. Okay, and if you know the charging of the capacitor, discharging of the capacitor, then it will be easily will understand this one here. Integrating type voltmeter, that is called voltage to frequency conversion method, we are going to call that. So this is the block diagram we are going to use here. Integrating type voltmeter here. This is the block diagram here. See what it is going to do. Road number 1 is joining. So the input voltage is given here. and that input, same input voltage is given here to the integrator here now. So this, it is going to integrate the input signal and give to the level detector. It is going to detect the level here now, and that one given to the pulse generator gate here now. To give the signal to the pulse generator, we have used one gate pulse here now, that is oscillatory here now. So this pulse, what it is going to give, if both the pulses are high, then what will happen here now? It is going to give the pulse generator output will be given. That output is given to the main gate here now. This is pulse generator gate. This is the main gate here. So to count, the counter will get whenever the main gate is open, then it will get the signal here now. And main gate is closed, then there is no signal here now. How it is? It is depends on this one here now. The pulse generator gate is open, then the pulse output it is going to give. It is going to compare with start and stop gate here now. Main gate, the main gate operation will be controlled by this gate here now. Should how to start the operation or stop the operation, it is going to give based on the time based selector here now. For that reason only the name came voltage to frequency conversion here. Voltage to frequency conversion. The clock oscillator we have used here, that is given to the one time based selector, and another one is pulse generator gate we have given here now. So why the name came here integrating type? We are going to use the integrator block here. Now this is the heart of the this block, sorry, this diagram or this instrument. For that reason the name came as integrator type digital voltmeter. Just a minute. So this is the block diagram. See here the waveforms we are going to use here now. This is at the start of the waveform integrator output we are going to get when it is compared here. Level generator detector it is going to compare. After that it will start the output here now. See here it is going up here now. After reaching to the certain value, what will happen? I will give the pulse generator off here now, and that condition what will happen? The voltage will start to decrease here now up to this pulse generator output here now. This is the pulse generator output here. When the pulse generator is off, then it is going to start to decrease. Again, when the pulse generator is on here now, here it is on, then it is going to attenuate the level detector. It is going to give the output here. So like that it is increasing and decreasing here now, increasing, decreasing. The slope type output we are going to get here. A constant input voltage is integrated here now. Whatever the constant integrated or input is there, that is integrated, and the slope of the output ramp is proportional to the input voltage. This whatever the slope is there, this is the input voltage we are going to consider here. We are getting the slope output of this one. The integrator output is this one here now. So thus this slope it is going to indicate that is the whatever the measuring value input we have given, that one we are going to call it. When the output reaches a certain value here now, it is going to reach the certain value, then it is discharged to zero here now. It is discharging to zero here now, and another cycle begins here from, see, I will take start from here. Just a minute. I'll take the marker. It is starting from here. So 0, it is going to increase here now. During this one, the charging will be occurred, the capacitor charging. Once the capacitor charge value is equal to this input ER here now, then what will happen? It is going to start to decrease here now. So we have given a pulse generator stopped here now. Okay, on that condition, so input will, sorry, whatever from that one, it is going to 0 here now. It will go to fill from the higher value to 0 here. Next, after some time, what we do after discharging to 0, it will start again. The next cycle will start, and then it will come 0 here now. Again, next cycle will start. Like that here, number of cycles it is going to complete here now. Based on that, the number of cycles per second, that is called frequency, we are going to call. So here, see here, slope 1, slope 2, slope 3, like that we have considered voltage to frequency conversion we have done here. voltage to frequency done here. So in the previous, the diagram, I have shown two diagrams actually. This is the block diagram. This is the working diagram actually. This one I have not explained. I will explain here. Before this one, we'll start here. See here, the voltage frequency conversion here now. The time taken to charge here now, T1 we have considered. That is, and T2 for the discharging we have considered here now. So the conversion, that is input voltage to the rated voltage. That is up to the rated voltage, this one. This is ER we are going to call. Whatever this one is that is input voltage, which is equal to input voltage we have considered. So EI equal to input voltage equal to output voltage into T2 divided by T1. Total time of this one is T1 here now for the input voltage here now. So that one we have considered EI is the input voltage equal to the ER time taken to discharge divided by time taken to charge here. This is the formula we are going to use. How the input voltage we are going to measure in the frequency, I will show you another formula. Before that, we will discuss this diagram here. See, this is the block diagram actually. This one is the circuit diagram here. This is the circuit diagram. What we have considered here now. So the input voltage produces a charging current here now. Here we have considered that is EI. EI we have given here now. This is EI. EI and here R1 is there. So what is the current flowing through this one here now? Can write the formula. Here this is the voltage. EI is there. Here R1 is there. We can write the current here now. We know the voltage, we know the resistance. What is the formula for current? I'm asking to you people only.
V upon R.
V upon R. So this E1 by R1, that is called current here now. So that current we have written here now. The input voltage produces a charging current, that is called EI by R1 here now. So this current, what it is going to do, it is going to charge us the capacitor here. It is going to charge us the capacitor here now. So that charges the capacitor, see, to a reference voltage, that is called ER. We have taken here now the reference voltage here now. We have taken here, that is called the reference voltage here now. When this ER is reached here now, so the comparator, what it will do here now, if it is this one equal to this one output here now, on that condition, the comparator, it is going to compare and changes its state here. Its state, it is going to change. So as to trigger the precision pulse generator, so the pulse generator produces a pulse of precision charge content that rapidly discharges here. Previously it is on the comparator because E out equal to the output of the integrator is less than ER, then it is on. If it is equal to R, ER equal to E naught, on that condition it is going to off here now. So the pulse generator will produce us here now. So it is going to stop the gate over there. So what will happen? The voltage will be decreases on particular. So while decreasing that one, the whatever the capacitor charged is there, it is going to discharge here now. That is going to discharge here now. So charging voltage is charged voltage is ER previously. So ER is discharged to 0. Then again the comparator it will give the changes its state and next cycle will begins over there. So previously the capacitor will charges here now. If ER equal to E naught, on that condition the comparator will changes its pulse and the pulse is given here now. So on that condition it is going to discharge here. It is going to discharge. Next it is going to compare and it is after discharging again the comparator will changes its state and then it is going to increase over. Then it will discharge. Like that it is going to give the signals over there. So based on that, the charging time, that is called T1 we have considered, and discharging time we have considered, that is called T2 we have considered. Charging time is T1 and discharging time is T2 we have considered. So but in the case of ER, that is called reference voltage, and T2 are constants here. So for that reason K2 equal to ER, that is called reference voltage into time taken to discharge. We have considered that one as K2 here now. That is called constant K here now. Constant K here now. So EI is the input voltage. Input voltage equal to, that is we know the formula ER T2 divided by T1 here now. So already ER and T2, these two are constant, means we can write this one as K2 here now. It is a constant here now. What is the frequency formula? F equal to 1 by T. Yes or no? F equal to 1 by T. This 1 by T1, we can write this one as output frequency output here now. So input voltage is equal to, this is constant here now. So the output only directly, whatever the voltage is there, that is proportional to the input voltage, that is EI is directly proportional to the F naught. We have proved this one. Yes or no? 1 by T1 I will write as F naught here now. That is output frequency, we can call that one. All of you know that one, time period 1 by T equal to frequency and T equal to 1 by F. Yes, correct?
Yes, sir.
So like that, the output frequency is proportional to the input voltage here. The output voltage is, input voltage is proportional to the output frequency here now. So the digital voltmeter has disadvantage that it requires excellent characteristics in linearity of lamp here. Lead is not linear actually. So linearity for purpose, it is excellent characteristics is required. This is the disadvantage. And the AC noise and supply noises are averaged out here. Now we are going to averaging the AC noise and supply noise here. So the output frequency is proportional to the input voltage. We have proven this one here. So the title also we have taken like this only, same. I will show here. This one, voltage to frequency conversion. What we have given input voltage. What we are going to get here output, that is called in the form of frequency. We are getting here. We are getting in the form of frequency here. So this is the construction and working of the operation of that integrating type digital voltmeter. Integrating type digital voltmeter. Any doubts? Any doubts?
No, sir.
So the third one will go that one, that is called dual slope integrating type. That is called the slope. We are going to use dual here now instead of one. See, in the integrating type, what we were considered here, where it went. So the slope, it is going to increase and suddenly it is going to drop into 0. Again, it is going to increase, dropping to 0 here now. Not like that here now. So here, dual slope, it is nothing but it is going to increase here now. And in the same linear level, it should have to decrease here. Like that, it is a dual slope here now. This is one slope, this is another slope we are going to call. So the name is dual slope integrating type digital voltmeter here now. This is also voltage to time conversion. That is nothing but voltage to frequency only. Na? 1 by T we are going to call, or 1 by F we can call that one here. So the dual slope integrating type digital voltmeter, in ramp techniques we are going to use. Superimposed noise can cause the large errors here. Whatever the superimposed noises are there in the previous one, that one we can remove here now. In the dual ramp techniques, noise is averaged out by the positive and negative ramps here. Here we are going to call this one as positive ramp and negative ramp here. Now positive ramp, negative ramp, like that we are going to use that one. Ramps using the process of integration here. Integration we are going to do here. Now the block is, I think here, it is there. Frequency by frequency converters we are going to use. See here, this is the dual slope we are going to use. The slope proportional to the EI, slope proportional to the minus reference we have considered here. This one minus reference voltage we have considered here. So the input voltage EI is integrating here now. Same like a integrating type explanation is there. That is integrated and it has started from here. It is charging here the capacitor and it will go up over there. So integrated output proportional to the test input voltage it is showing here now. After a fixed time, after T1 here now, that is a fixed time is there. So equal to T1, the input voltage is disconnected here. Now we are going to disconnect the input voltage here. Okay. And the integrator input is connected. That is called negative reference voltage we have taken here. Now that one we are going to connect here now. So that is called the integrator input is connected. We have to remove the input and integrator input we have connected over there. So the integrator output will have the negative slope, which is constant and proportional to the magnitude of the input voltage. It is constant and proportional to the magnitude of the input block. Magnitude is same only here now. For the 1, 2, 3 slope 1, slope 2, slope 3 we have taken here now. So different time is taken to slope for the charging, that is called, that is same only for the input. For the output reference voltage, the time is different for each block here now. See here, the magnitude is same, but whatever the duration is there, that is different durations we have used here. That is T2, T2 dash, T2 double dash we have used here. With the block diagram, we will do that one here. No, see, this is the block diagram. We have used again same integrator capacitor. We have used one comparator, that is called zero detector. If the output is 0, it is going to on, and for that reason detector or comparator E0 and this ground we are going to compare here now. Here the gate we have used, the oscillators we have used, and counter, and it is going to count the times here now. Frequency by frequency, it is going to reset that one here now, and it is going to switch drive here now. Switch drive means for this switch operation, it is we are going to use this one here. So this one F by F, it is going to give the signal, that is logic 1 is there, then switch 1 operate, switch 2 for the 0, like that it is going to give the logic here. See here, for the T1 and T2, it is going to operate this integrated block. At the start, initial condition, see, we have taken that block. I will draw here. Just a minute. Both fast away. Okay. Here, to take like this. So this one I will use dotted line better. This is T1 we are going to use, T1. At the start, it first resets counter and this frequency by frequency outputs logic to 0 level here. At the start, we have set this one as 0 and this counter also we have set it into 0 here. When S1 is closed here now, because of this switch drive, what it is going to do, it is closes here now, and reference voltage it is open here. So when SI is closed, S1 is closed, then the input voltage is applied here. Okay, so here the resistance is there, some current will flow here now because of this EI by R current. The capacitor will charge us here now. The capacitor begins to charge here now. Okay, as soon as the integrator output exceeds the 0 here, how the capacitor charges, then as soon as the output voltage, this one here, exceeds the 0 value. So the comparator output voltage changes its state here now. It is going to, so at the initial capacitor will charges here now, up to when it will reaches here, the input block, whatever the comparator block is there, it is changing its state. It is going to change that one, which opens the gate so that oscillator clock pulses are fed to the counter here. It is going to open the gate here now. Whatever the gate is there, it is going to open here now. So whatever the oscillators are there, oscillator clocks are there, it is going to fed to the display and counter here. So which opens the gate so that oscillator clock pulses are fed to the counter here. Whatever the blocks are there, it is fed to the counter here. When the ramp voltage starts here now, see, this is ramp voltage we are going to consider. That is gate open and close we are going to consider. Ramp voltage means this one here. Okay, when ramp voltage starts, the comparator goes to state 1 here now. This, it is going to go to state 1. The gate opens and clock pulse drive the control counter here. Right? If it is 1, it is going to open this one here now. So on that condition, it is going to give the clock pulse here now. When the counter reaches to maximum count, it is going to count here now 0, 0, 0 we are going to use. Maximum count is nothing but 99999. We are going to consider that 9999 decimal numbers here. It will reaches to maximum count here. That is, the counter is made to run for a time of T1. In this case, the 999 is there. So for the T1, it is going to increase. It is going to charge the capacitor. Okay, on that condition, the comparator is 1. That is nothing but it opens the gate here now. It opens the gate and it is 1 here. And the next clock pulse, that is called, goes to 0, 0, 0 and counter activates F5F logic to 1 here. So this counter for the next it is 1 is there. So it is giving the T1 operation. When it is 0, when it will reaches to value, it will 0, it is going to close this one, and on that condition the output count will be 0. So the F and F logic will become 1. On that condition, what will happen? It is opens the SI switch. S1 switch will be open and SR switch will closes here. The SR switch will closes here now. That one only they have told. F1, F2 logic level 1. Detail in detail they have not mentioned. Just a minute. I'll go to the next slide. See here, this activates the switch drive that is called EI is disconnected. This is going to disconnect and ER minus ER is connected here now. So we are going to connect the minus reference value. We are going to connect here now. So that is connected to the integrator. It is going to connect. This integrator output will have a negative slope, which is constant. And the integrator output, now what it will happen because of the negative slope, it is going to start to decrease here. It is going to start to decrease here now. The integrator output will have to negative slope, which is constant. That is, integrator output is now decreases linearly to 0 volts. It is decreasing to 0. Yes or no? So initially when EI S1 is closed, on that condition gate is open, then it is going from 0 to up value, higher value. When the comparator output goes to 0, on that condition it is coming to the 0 here now, the integrator output. The comparator output state changes again and locks the gate here now. Again, what it will do, it is going to lock the gate here now. So the discharge time T2 is now proportional to the input voltage. Here, this time we are going to consider as T2 here now. So this is proportional to the input voltage here now. The time is, so because voltage to time we are considering here now during T2 here now. So T2 is now proportional to the input voltage. The counter indicates the count during the timer T2 here now. It is going to give the count here now. When the negative slope of the integrator reaches to 0, the comparator switches to 0 state and close the gate. Gate closes here. Now it is going to 0 means it is going to close. 1 means it is going to open here. That is, the capacitor C is now discharged with a constant slope here. Now, whatever the capacitor charging is there, it is going to discharge here now. So as soon as the comparator input detects 0, that counts E0 is 0, the counter is stopped and the pulses counted by the counter thus have a direct relation with the input voltage here. So the concept is very simple here now. Itna explanation karke kuch fayda nahi hai. I will tell you in simple way, okay, as it is. So during this input EI, the capacitor will start to charge here. On that condition, what will happen? It is going to, the gate will be 1 here now. The gate will be 1. It is opens here now. So this count, it will count as 9999. It is going to count here now because the time oscillations we have given here. So on that, during the time T1, it is going to increase here now. Once it reach to the reference value, that is 0 comparator is compare and it will give the output over there. So it will provide, it is going to change its states to 0. 0 means it is going to close the gate here now. So close the gate means the output will be 0, 0, 0. On that condition, the logic of this one will become 1. Initially 0 there. After that one, it will be 1. And this switch drive, what it is going to do? This S1 switch, it will opens and SR is closing here now. The minus it is going to consider. So during this minus input, whatever this capacitor charge is there, that is going to discharge to 0 here. That is called, that is T2 we are going to call here now. So the time taken to discharge, that is called, the total is proportional to the input voltage we are going to call it. So the voltage to time conversion we have discussed here now. That is the output. Starting only we have the name it was there. Just a minute, I will show that one. Very good. In the starting we have taken, that is here voltage to time conversion here. So whatever the voltage is there, that one we have considered in the form of time, that is called, see here only we have mentioned that one. So where it is, the comparator output state changes here now. The discharge time T2 is now proportional to the input voltage here. Input voltage. This is just theory explanation here. So we have some equations also, same equations we are going to consider. Some different equations are there that you have any doubts here means you can ask. Up to here, if you have any doubts, you can ask me. Then we'll go for the equations. I'm asking to you people only. If you have any doubts, you can ask me.
No, sir.
Just you are attending for formality then. Okay. So during the capacitor charging, the output of the capacitor, that is called output voltage, E naught we are going to call here now. That is called minus 1 by RC here now. So we have considered this resistance and capacitance of this capacitors, that is minus 1 by RC. And during the charging, what is the time duration? The time duration we are going to consider from 0 to T1 here now. 0 to T1 is the charging. So the integration limit we have kept as 0 to T1 we have kept here. So this is resistance, this is capacitance we have considered minus 1 by RC. So what is the input voltage? EI here now. EI with respect to T we have to the integration here. So EI I will keep as it is here now, and EI by RC also I will keep as it is here now. So integration of 1 with respect to T, what is the answer? Integration of 1 with respect to T, that is called T only we are going to get. Yes, or integration of X.
Yes, sir.
So the limits they have given here now. One side is 0 is there, another side is T1 is there. So we can write here now T1 minus 0. Yes, T1
Yes,
minus
sir.
0. T1 into EIRC, that is called minus EIRC into T1, and 0 into anything, that will become 0 only. So minus 0 we can write here now, big C. Yes?
Yes,
0
sir.
into anything 0. Okay. This is one term. This is one thing here now. Next, this is for the charging. We have derived the equation here. This is only for the charging condition here now. This is for the charging here now. Next, similarly for the discharging time taken here, that one we are taking reference here now. So that is called T2 we have considered here now. 0 to T2 here now. This one is 0 we are going to consider, and 0 to T2 here. So the integrator limits we have taken as 0 and T2 we have taken. Again here 1 by RC minus ER, that is minus supply we have given here now. Remember the circuit diagram we have given, that is one is EI we have given, another one is minus ER we have given. Yes or no? Two inputs are there. So minus ER we are going to reference output we are going to consider here. The switch changes it to minus ER. So this is the input we have given here. So during this condition, again this ER is a constant here now. So minus ER and 1 by RC will keep separate here now. We'll separate this one here now. Again, the integration of X with respect to dx. Sorry, the integration of 1 with respect to dt. That is called T only. Again it is T, and the limits is 0 to T2 here now. So we'll get that one, the output answer will get that one, T2 minus 0. Yes, we get T2 minus 0.
Yes, sir.
So on that condition, T2 into minus ER RC. So minus ER into T2 divided by RC. One term we have written, and in minus this one minus I will return. This ER RC into 0, that is nothing but 0 only will get here. 0 only we are going to get here. So this equation is for discharging here. We have got two equations, one for the charging, another for the discharging. Two outputs are there. This is the for the charging, this is for the discharging. Like that we got two outputs here. Now two equations we have derived for the charging here now. This is for the charging and this is for the discharging here. Both the equations we have derived now. What we have to do, we have to subtract the discharging equation from the charging equation here. In this charging equation, this one we have to minus here. We have to do the minus here. So LHS to LHS, RHS to RHS we are going to do here. Next, first what I will do, I will subtract here now. That is E0 minus E0. That one E0 minus E0 I have written here now. E0 minus E0. And this one will consider minus ER T2 RC here now. Equation number 2 we have considered here now. That is this one. Minus, I have used minus. Subtracting we are using means I have used minus. And I'll use the open bracket here now. And here minus is that minus EI T1 RC. EI T1 divided by RC we have written here. Okay. So next thing what will happen? E0 minus E0. What is that answer? E0 minus E0 equal to 0. Yes or no?
Yes, sir.
So 0 we can use here no. Equal to. See here minus ER T2 by RC is there. I will write as it is here now. Minus ER T2 divided by RC. This one minus into minus. What is the answer? Here one minus is there. Here minus is there. Minus into minus. Minus into minus. What will become?
Plus.
Plus here now. So I will use this one as plus here now. Plus EI T1 divided by RC here. Divided by RC I am going to use here. Next what you do, here 0 is there. Here minus is there. I will send this term into LHS side. So this minus term I will send into LHS side. It will become plus or minus? Plus. So on that condition, ER T2 RC equal to EI T1 RC here. It will become like this only. Yes,
sir.
ER T2 divided by RC equal to EI T1 divided by RC here. So this equation we got here now. Once we got this equation means to check that one, which one is cancelling and what is the left term here. ER is there here, if there is no ER term. T2 is there is no T2 term here. Here EI is there, EI term is not there. T21 term is there, even here. See here also RC is there, here also RC is there. We can cancel or we can multiply. 1 by 2 equal to 1 by 2. Can cancel that one?
Yes, sir.
So here RC will get cancelled. This RC will get cancelled here. Now we'll get the equation like this. ER T2 equal to EI T1 here. EI T1. So from this one, can you write the equation for the EI input? Which one is input here? No, input voltage is EI here. So EI equal to ER T2 by T1. This T1 I will send into LHS side. It will become denominator. No. So EI equal to ER T2 divided by T1. You can write like this. Yes.
Yes, sir.
So previously you compare with previous one. That is integrating type. Same equation we were received over there also. There be same equation aaya ER T2 by T1. So this ER T2 we are going to consider as constant here. No. So T1 is nothing but that is called time period. 1 by T1 we can consider as time period. That is called frequency. We have considered in the previous derivation, previous explanation. But here the time period only we are going to measure here. No. So the input voltage EI equal to ER T2 divided by T1. This is the equation we have derived in the period of time. Check that now. Next what we have to do, if oscillator period equals T here now, time period, then the digital counter indicates N1 and N2 counts here now. What they are telling here now, instead of this T2 equal to, we can write T2 equal to, that is in the time period we have to consider. So T2 equal to N2 into time period T we have to consider here now, and T1 equal to N1 into T we have to consider like this. N1 into T we have to consider like this. Substitute these two. T2 value में N2 T we have to substitute. N1 place, in the place of T1 we have to substitute N1 here. Previous equation you check it. Here it is there. Here T2 is there. I will substitute N2T. Here T1 is there. I can substitute N1T. I will substitute here. By substituting this one here now, that is TT gets cancelled here. Yes. TT will get cancelled. Here also T is there.
Yes, sir.
Here also T is there. That is called EI equal to N2 by N1 into ER here now. So now the N1 and ER are constant here now. This N1 and ER are constant. So that is called K1. We are going to call that one. That is K1 here now. So then EI equal to N2 here now. N2 is nothing but that is called, they are telling counter indicates N1 counts here now. Count is nothing but time here now. So that is EI, the input voltage is directly proportional to the N2 counts. You can say that one. You can say that one. Previously we were used that is called ERT2, K2 equal to ERT2 as constant. But now here we are using ER divided by T1, we are using as a constant, that is called K1 here. So very clear, both the intentions are same only, but we have to use different constants we have used. Here K1 we have used, so in the place of K1, N1 we have used. But previously we have used K2, that is called T2, we were using that one. So that one you have to remember that here. Just a minute. So from equation number 5.3, 5.3 means this one, from this equation, you can say that it is evident that the accuracy of the measured voltage is independent of the integrated time constant. Whatever the accuracy is there, that is independent of integrated time constant. It is not dependent on the integrated time over there. The times T1 and T2 are measured by the count of the clock given by the numbers N1 and N2. This T1 is given by counted by N1 and T2 is counted by N2. So the clock oscillator period equals to T, that is called time period. And if N1 and ER are constant, then that input voltage, that is accuracy of the method, is also independent of oscillator. This equation, that is accuracy, and it is also independent of the oscillator. We are going to tell that. The dual slope technique has excellent noise rejection here. Now the main advantage of this one is it is going to reject the noises here. Now it is going to reject the noises, and superimposed AC are averaged here. Now we are going to average the superimposed AC here. Now the process of integration, the speed and accuracy are readily varied according to the specific requirements. Also the accuracy will vary plus or minus 0.05%. in 100 milliseconds is available here. 100 milliseconds available, 0.05% it is accuracy is there here. So this completes the integrated principle of dual slope integrating type digital voltmeter. So we have discussed three types of that integrate ramp type digital voltmeter, integrating type, dual slope integrating type we have discussed. Another two types are there. That one we will discuss in the next class. We'll discuss in the next class, that is successive approximation, and another one is which is continuous balance type. These two will discuss in the next class. I will stop here only and we will continue in the next class. Rule number 11, rule number 15, 17, 19, 24, 25, 27, 29, 31, 34, 36, 37, 38. These are the absent numbers. Anybody is there, you can tell that one. Okay. Yes. Rule number 4. Aishwarya. Aishwarya, anything you want to ask?
No, sir.
Okay, we'll stop here only and we'll continue in the next class. Maybe tomorrow, today I may get one more. We'll see that one. Now I'll put the link on that one. Okay.